Alright. So today exercise will be slightly different compared to last week. Still, the outcome, the objective for this lesson is the same, to develop mathematical model for chemical processes. However, in this case, I still use the blending system, but a little bit few adjustment has been made. So based on this, you can see that the case study used still a blending system, where in this blending system there are two streams, 1 and 2 are being mixed in a well stirred tank, producing a product stream 3. The first feed stream is composed of two components, A and B, with mass fraction XA1, XB1. So when we have the mass fraction, still in this case is kilogram. Kilogram over kilogram, the mass fraction. Or sometimes maybe you can assume gram over gram. It's okay, as long as it represents the mass fraction units. Only in this case, the second feed stream consists of component A only. There is no component B. So meaning that the second stream, which is the stream number 2 here, is what we call it pure component stream, where the SA2, since it's a pure component, SA2 become 1. So the XB2 automatically becomes 0. So this is one of the different compared to the previous blending case study. Roughly, when we take a look, it's like the same, 2 input, 1 output. But in this case, there are few adjustments. The first one is the second feed stream consists of component A only. There is no component B. And then let's go through the second paragraph. Let F1 and F2 be the volumetric flow rate. If you recall, based on the last exercise, F considered as the mass flow rate. Now it's changed to the volumetric, meter cube over minute. And T1 and T2 is their corresponding temperature. So T1 and T2 is the inlet temperature for both streams. And it has been assumed all flow rate remain fixed and operating under constant volume. So since we have F1 and F2 as our inlet flow rate and the F3 represent the outlet flow rate. So this flow rate remain constant. So meaning that if we have the value, it does not change. So it become constant value. So when you have a constant value, then this contribute to the constant volume. How it is contributed, we will see later during the overall mass balance derivation. So in this case, that XA3, XB3, F3, and T3 be the composition, flow rate, and temperature of the product stream. So other than that, it remain the same. One thing that you can notice from this given blending system, there is no coil. No coil. No coil in the system. No coil in the system. So that means when there is no coil, there is no heat addition or heat provided to the system. When there is no heat, that means you don't have any Q. Q in this case become 0. So this is the thing that you need to have some flexibility, some understanding how to include the term, how not to include the term. If we compare with the last week exercise, there are some differences. The first one, second stream. Pure component of A. There is no component B. in the second stream. And then you can see that the flow rate used are volumetric. It's not mass. Compared to the last case study. And then in this case, you also mentioned that you have the fixed flow rate. When you have a fixed flow rate, then you have the assumption of the constant volume. And lastly, there is no coil. No coil. No coil given in the diagram. So that means there is no Q provided, no additional heat provided to the system, which contributing no variable of Q. So Q becomes 0. See, so this is the different information given for the new case study here. Although you have the same operation, which is blending system, but the variable, the assumption used are different. When you have different assumption, this contributing to the new mathematical model. So let's take a look one by one how the balance or the mathematical model for the given system is different. We start with the common one, which is the conservation of total mass. So in this case, still, we do some revision about the conservation, because this one is, for me, is quite fundamental. So you need to acquire this knowledge. So the term for the total mass is starting with the rate of mass accumulation. Again, this one, if we try to derive it, you can have the dm over dt, where the m, let's say here, is for the mass. So mass, let's say you have the kilogram, and t will be your time, let's say in the minute. So for this part, the unit on the left hand side will be kilogram over minute, equal to rate of mass in. Still, this one, m dot in minus m dot out. Still the same thing, where the m dot represent the rate of mass. So supposed to be on the left, on the right hand side, the unit should be kilogram over minute, for example, for the mass over time. So for this part, we can further expand our equation, where the m can be related with the density and the volume. M equal to density multiplied by volume. There you will get the d rho v over dt equal to m dot in. So based on this case study, you have two inlet coming into the system, where this inlet has the volumetric flow rate. So you have the F1 plus F2 minus F3. So this is the flow rate coming and exiting the system. However, if we refer back to the given statement, the F1 and the F2 is the volumetric, where the unit of volumetric given is meter cube over minute. So this means if we just use the F1 in this case, we will represent the inconsistency of unit, because this one is meter cube over minute on the right hand side, but on the left hand side is a kilogram over minute. So the unit is not consistent. What we need to do is to make sure the units are consistent between the left and the right hand side. So in order to make sure we have the consistency of the units, then that means we need to multiply the flow rate, the volumetric with the density. So for this part, we multiply with the rho 1, rho 2, and the rho 3. So when we multiply the volumetric with the density, you will get the kilogram over minute units. So let's say in this case, the density is the kilogram over meter cube. So you cancel meter cube, you get kilogram over minute. So now the units are consistent. So this is the thing that we need to emphasize. If the units are not consistent, then all of the mathematical model developed will be inaccurately representation. You will get the wrong mathematical model. So better we check the unit first. Once we have the unit consistency, then we can proceed with the further derivation. Any questions so far?
No, sir.
All right, so let me continue. So we have the d rho v dt, then we have to expand the equation. So you have the rho dv dt plus v d rho over dt equal to rho 1 f1 plus rho 2 f2 minus rho 3 f3. So on the left hand side of the equation, you have two differential terms, dv over dt, change of volume against time, and the change of density against time. So in this case, we agree that the density will not be changed against time. So this one, the second term, normally will be neglected because the value of the density is remain constant. So when it is remain constant, although your time is changing, but it will produce the zero value. And then, based on this case study, it also mentioned that the flow rate remain fixed and operating under constant volume. So based on this statement, this indicate that the volume is not going to change. So when your volume is not going to change, then this contribute to the dvdt equal to 0. You still have the volume, but the value of the volume is constant. So when the volume is constant, then that means it's not going to change. Then when you have the derivation of dv over dt, automatically it becomes 0. So that leaves you the 0 term on the left hand side. Then you have the right hand side, rho 1 f1 plus rho 2 f2 minus rho 3 f3. So this can be further rearranged. Let's say you can have the rho 1 f1 plus rho 2 f2 equal to rho 3 f3. So in this case, we have density for each stream, inlet and outlet stream. So for the process controls, normally we can do the assumption, where in this case we assume the density for each stream can be remain the same in order to simplify our equation. Although we agree that all of the component has its own density, but in this case, for the mathematical model, we can further simplify the equation by equaling the value of constant for each string. So now, if we assume the density of 1, 2, and 3 are remain constant, has the same value, then you can further simplify your equation to become F1 plus F2 equal to F3. So this represents your mass balance, where this one normally we call it in equal to out. So where F1 is your in and then F3 is your out. So in equal to out, or we refer it your mass balance under steady state condition. So that means your overall mass balance does not have dynamic model. It just has steady state model. It's different. Dynamic model, normally in the dynamic, you need to have the change against time, where let's say you have the dv over dt. So this is what we call it dynamic. But in this case, you only have steady state model because your value of flow rate and the volume are remain constant. So although the time is changing, still you get the same value. So this contributing to the steady state model obtained for the given blending system. Any question so far?
Doctor,
Yeah.
what happened if the volume is not constant?
What happened if the volume is not constant? All right. So let's take a look. In this case, I choose the different color to indicate. So this one, what has been derived is based on the constant volume. Let's say under different condition, the volume is not constant. Then you will start it from here. We agree that the density, of course, will be remain constant. Under no circumstances, under no condition, the density will be changed. So when you have the volume is changing, then you have the rho dvdt equal to rho 1 F1 plus rho 2 F2 minus rho 3 F3. So you will have this kind of model. Still, we can use the same assumption where the density will be remain the same. So this one is fixed. It's fixed assumption. You can use it throughout this subject where the density for all stream remain constant. So when you have this one, then you can simplify by cancelling or eliminating density on the left and the right hand side. So this contribute to the dv dt equal to F1 plus F2 minus F3. So this is the dynamic model for your overall mass balance. In the case of, yeah?
May I ask for the left-hand side, the density is referred to which density there? Because on the right-hand side got 1, 2, 3, but for the left-hand side it's just like rho, then what is the density referred to?
Okay, thank you. All right, now, in this case, if you take a look on the first line here, you can see there are 4 density available. The first one, the row 1, row 2, row 3, we agree that it represent the stream. Where in this case, if we refer back to the stream number, we can say that in here, you should have the row 1. In here, you should have row 2. And this one, stream number 3 is the row 3. How about the density, the row only without numbering? Normally, if we refer, this one refer to density multiply with the dV over dt. We take a look, where is the volume? The location of the volume is inside. So this is your volume. Then the density without the numbering referring to the density inside the volume, inside the tank. So, or what we call it, the density of the mixture when you blend two different streams. So in this case, normally, if you don't have the number, the label of the variable, for example, like this one, like the density, or here the temperature, you don't have the label. So normally this one represent the density or temperature inside the solution. So back to the question asked by your friend. So here the density indicate in this part referring to the density in the solution. While for the row 1, row 2, row 3 represent the flow rate, density in the flow rate.
Doctor.
Yeah.
Does it mean the row without the numbering is also is same as the row 3 because it come from the volume, right? And the volume is come up at the stream 3. So that means it's the same.
Yes, correctly. What you already trying to say is the density inside normally will go exit the system through the stream number 3. And of course, this one sometimes we can say that since you have the well mixed solution, well mixed because of the presence of your stirrer, you have the well mixed solution. Then the density inside will exiting through the exit flow rate. So we can say that the rho equal to rho 3. The same goes with the temperature, the T equal to T3. Only in this case, we cannot say that the T1 equal to T2 equal to T3. We just assume as overall, the density inlet is equal with the density outlet. It's not going to influence very much. The density will not give the direct impact on your mathematical model. That's why in this case, we further extend the assumption to include the inlet.
And Doctor?
Yeah?
If we take a look at the previous studies and that we have learned in the theoretical model use, in that theoretical model you still have the row on the theoretical model. So in the previous model, can we also neglect the row and V and CP in that theoretical model?
All right. So in this case, let me refer back to the previous exercise, previous derivation, in order to have a clear picture of what has been asked by your friends. Just a moment, let me find the file. Okay, let me share you the file. Alright. So if you refer back to my notes based on the last week class, this is your case study where the F is given in the mass flow rate. And then we did the conservation of total mass. And finally, you get the following equation. Rho dVdt equal to F1 plus F2 minus F3. So this is based on the last week exercise. And this week exercise, you don't have the density on the left-hand side. Why?
To have the constant units.
Consistent unit. Yeah, correct. So in this case, you cannot neglect the density on the left-hand side because the F here used is the mass flow rate. That's why on the left-hand side, you need to multiply with the density. So this is the thing that I want you to familiarize. Although the variable looks similar, but it contain different meaning, different term. For the last week exercise, is mass flow rate, where the F is based on the kilogram over minute. So in order to have a consistent unit on the left and the right, that's why on the dVdt you multiply with the density. And then there is no density multiply with the flow rate because the unit is already consistent. But for today's class, if you refer back, in this case, you can see on this equation, for example, you multiply the density with the dVdt and also you multiply the density with the flow rate. Why? Because unit. In this case, the flow rate, although you have the same symbol, but is represent volumetric. So you have a different term in the end. So that's why I'm giving this exercise. I adjust a little bit because I want you to make sure. Although you have the same case study, but in the end you may get different mathematical model. Any question relating to this?
No, doctor.
Just for all of you, it's better if you have some curiosity, you don't understand, just feel free to ask. I'm not going to mad at you or not. Don't worry about that. It's my job to ensure you have the complete understanding. In order to enhance your, or in order to solidify your fundamental toward this subject, it is essential to have the complete understanding. And if you don't understand, feel free to ask. We can have the discussion on this.
Doctor,
Yeah.
the V on the left hand side for the volume is not constant. Do we need to expand it?
Okay. All right. So in this case, the volume is not constant. The green color, I end with the dV over dt. Of course, this one can be further extend the equation to represent the level, where here you can have the V equal to AH. So when you try to substitute into the equation, you may get A dH dt plus H dA over dt equal to F1 plus F2 minus F3, where the dA over dt, the change of area against time will be neglected, 0. So you get this kind of mathematical model. So when to know, how to know, either you need to stop at volume or the level. Normally we specify in our question. let's say the question just ask you to develop the volume mathematical model for volume, then you stop at divinity. And if the question asks you to develop until level, then you further extend it to include the level inside your equation. So any other question relating to the mass balance? So if not, then let me continue. So let's back to the original question, where in this case, the volume is changed, you get the in equal to out. So this is the equation represent the constant volume and constant flow rate. So we already complete the first part. Now we go to the second part, the conservation of the component. So in this case, if we refer back to our case study, there are two components, A and B. Only in this case, A and B represent both stream. And then component B only represent at the inlet, first inlet and the outlet. There is no component B in the second stream. So let's have a look on how the conservation of component can be developed. So in this case, we start with the component A, balance. So for the component A, we start with the rate of component I accumulation. I here represent your A component. So we start with the dMA over dt, where the MA in this case represent your kilogram of A, kilogram A, mass of the A, equal to rate of component I in, still in this one, I put it m dot A in minus m dot A out. There is no component I produced, there is no component I consume. This one is just a blending system. So you have the dMA over dt. So for this part, we need to represent the composition of the A. So MA normally can be obtained by mass multiplied with the XA, where the M is the total mass, kilogram. The XA is the kilogram A over kilogram total. So when you try to cancel it, you get the kilogram A. So this relationship can be further used in the model. So you will substitute the dMA with the dMXA over dt equal to m dot A in, the rate of mass component A coming into the system. So since the rate coming based on the flow rate, so you need to have the F1. F1, and then of course the F1 you need to have the XA1. So based on this, if we check the unit, F1 is the meter cube over minute. The XA1 is the kilogram A over kilogram. So since this one you cannot cancel it, kilogram, meter cube and so on, you need density to eliminate the meter cube. So you need to multiply with the rho 1, where the rho 1 is kilogram meter cube. So when you have kilogram meter cube can be cancelled, kilogram can be cancelled, you get the kilogram A over minute. It's like that. So we complete the stream number 1 and then you have the A in the stream number 2 plus rho 2 F2 XA2. The same term, only the different numbering. Minus rho 3 F3 XA3. So you have two inlet of A coming into the system and one outlet. So you have the X at each term. So we complete the inclusion of the term for the left and the right hand side. What we want to do next is to further extend. So for this part, the dm xa over dt. So m we know that is based on the density multiplied by the volume. So we can substitute the equation, become the d rho v xa over dt equal to rho 1 f1 xa1 plus rho 2 f2 xa2 minus rho 3 f3 xa3. So the left hand side you have the d in the bracket, you have the density multiplied with the volume multiplied with the mass fraction. For this part, based on the given case study, we know that the rho is constant. Where the rho here, based on the previous mass balance, we know that the rho equal to rho 1, equal to rho 2, equal to rho 3, equal to constant. So when we have like this, that means we can further cancel later on the term of density. And then for the volume, it is stated that volume also constant. So when you have the constant volume, in this case, that means we don't need to further expand our equation. So when we have density and volume is constant, that means we can take it out, the density and the volume outside the differential term. So you have the left hand side like this. Previously, all of the variable inside the differential term, rho VSA. Since the density and the volume is constant for this case study, then you can take it out. So that become the rho multiply the volume, and then you multiply with the differential XA over dt. Next concerns with the right hand side, you still have the same term. Minus rho 3 F3 XA3. So based on this, based on the given assumption where the density equal to density 1, equal to density 2, equal to density 3. So that means we can further cancel our equation, which leave us the v dxa over dt equal to rho 1, equal to f1 xa1 plus f2 xa2 minus f3 xa3. So you get like this. Now, in this case, almost complete. We have the volume dxa over dt equal to f1 multiplied with the xa1 plus f2 xa2 minus f3 xa3. The problem here is what is the xa here. On the differential term, you can see the variable of SA and where this SA belong. Unlike the SA1, you have the 1, SA2, you have stream number 2, SA3, stream number 3. So the SA here, the location, if we go back to the case study, the SA is inside the solution, is contained in the volume. Where, since you have the well-mixed solution, this SA will eventually going out in the stream number 3. So suffice to say that the XA normally can be approximated by XA3. Again, I repeat, XA in the term represent the composition of A inside the solution. So this solution is well mixed. So that means you have a uniform composition throughout the volume. And eventually, the liquid inside the tank will be exiting through the stream number 3. So that's why we can assume the XA equal to XA3. So the SA here, I located SA3. Alright. So this is what we call it component A balance for the given system. So I open to any question that you may have.
Hello, Doctor.
Yeah.
May I ask about why the SA is assumed is same as the SA3 because I still cannot understand about it.
Okay. Sure. Alright. So for this part, let me clear this part first. Alright. So now, if we take a look on our mass balance, component balance equation, you can see the variable of SA. So normally, the SA here is located at the inside of the solution. So this is your solution. So now the question is, why I assume SA equal to SA3? Why? So here we can see that you have the SA1 at the stream number 1, SA2 at the stream number 2, and the SA3 stream number 3. So here we need to see. Here you have the SA inside the solution. So you have the well mix, you have the stirrer. This stirrer function is to achieve the uniform composition of component A. So this means throughout the solution, you have the uniform composition of SA. So during the operation, you have the exit flow rate. This is your exit flow rate. F3, stream number 3, outlet stream. So meaning that whatever inside the solution will coming out through the stream number 3. That is the operation. Unless if we don't have the outlet, then what happened to your solution will be keep increasing. So in order to avoid that case, that scenario, then you have the outlet for it. So here the outlet for it have the SA3. Where this SA3 coming from? It must coming from the solution. It must coming from the composition in the solution. So since it's originated from the solution, then that's why you have the SA equal to SA3. It's like that.
Okay, thank you, doctor.
All right. Any other question? So if there is no further question, now we complete the component A balance. And since we deal with the two components, component A and component B, and in some cases we can derive the component B balance. Of course, since this one involve the XB and SA only, so we can say that SA equal to SB. We can say that SA plus SB equal to 1. So this is the thing that you can use for relating how to obtain the composition of B. And let's say in some cases, they ask you to derive the component balance and how it look like. So basically it's the same thing. Component B balance. We can start from here again, the dm over dt for the component B. Only for this part, we have the dmb over dt equal to mb in minus mb out. So for the mb, we know that it will connect to the m b equal to m xb, like the same you did in the component A balance, where we substitute the mxb inside the equation. For this part, we put dmxb over dt on the left hand side, and then for the right hand side, mb in. So for the mb in, for this part, it say that the first feed stream you have A and B. Second feed stream, you don't have any component A. You don't have any component B. So the presence of component B is only at the stream number 1. So you have the F1, row 1, XB1. And then minus F3, row 3, XB3. So there's a little bit different compared to the component A balance. Because in this case, the component B only available in the first stream and the exit stream only. So other than that, remain the same. So we can further extend. Here I just simplified a little bit. We know the density and the volume constant. So you have the d rho v dxb over dt equal to F1 rho 1 SB1 minus F3 rho 3 SB3. So again, we assume the density for each stream can be similar, thus constant. So this reduced to V dxb over dt equal to F1 SB1 minus F3 XB3. And lastly, since this one consists of the SB, so we apply the same thing, where the SB is located inside the solution of the tank, and in the end, this SB will exiting through the stream number 3 as SB3. So we put SB here equal to SB3 assumption. So that means you can have the V dxB3 over dt equal to F1 SB1 minus F3 XB3. So this is your component B balance. How to derive component A and component B balance for the given case study. If we take a look on the component A balance, you have 3 terms for the right hand side of the equation. But for the component B balance, only 2 terms, F1 and the F3, available in the right hand side of your equation. So you need to take a look. You need to verify where the location of the component. Sometimes it's not available in the each stream. Any question?
Doctor, for the component B balance, why the SB1 is not same as the SB and SB3? Because in the question is only mentioned that the SB is only at the first string only.
Alright. Why SB1 is not equal to SB3? Correct.
SB3 and SB.
Okay. In this case, if we refer back, let's say I just copy this one. Now, here, if we refer back to this diagram, why we cannot assume SB1 equal to SB3? Okay, just let's say we imagine it. We try to analyze qualitatively. Let's say, for example, in this case, SA1, we put the value for better illustration. Let's say SA1 here 0.5. SB1, of course, 0.5. So for this part, SA2 equal to 1. SB2 equal to 0. So when we mix both stream into 1, then that means since you have the SA2 equal to 1, we can say that SA3 will be increase or decrease.
SA3 will be lower than the SA2.
Yeah, it will be lower than SA2, but it will be higher than SA1, correct? Okay, so this means your SB1, SB3, what happened?
SB2 will be decreased.
Will be decreased, yeah. So SB3 should be less than the SB1. Then we cannot assume the SB1 equal to SB3. Although you have only one inlet and one outlet, because the mass fraction will be different. So here the SB1
After
will not be equal with the SB3. So that's how you need to familiarize. Sometimes maybe we cannot imagine thing, but why don't you try to put the value in order to have why cannot be same? It's like that. Any other question? If not, then we take a break, and after the break, we will continue with the derivation of energy balance. So we break for 5 minutes. Okay, let's continue on the lesson for today. Again, let's revisit a little bit. So today we use the same blending system with a different assumption used. So when you have a different assumption, then in the end we will have different mathematical model. So this is what has been obtained in the overall mass as well as the component balance. So now we want to complete our balance, which covering the conservation of energy principle. So for this part, if we take a look on the system, we have the T1, T2 as corresponding temperature, and then in this case, the constant volume, and lastly, the absence of the coil. So how the absence of the coil impact our model. So this is what I want to demonstrate today. So let's begin with the derivation of conservation of energy, where in this case, we use the same equation, rate of energy accumulation, where this one will be the dE over dt equal to rate of energy in by convection, E dot in minus E dot out. E dot in, rate energy in by convection, and E dot out representing the rate of energy out by convection. So for this part, if you see there is no coil. So no coil, no heat addition to the system from the surrounding. So you have the Q equal to 0. So this means no Q. So this is the thing that you need to be aware. How to include the Q, on what condition the Q can be included. So here the dE over dt, this one I just simplified. The detail you can refer it to the previous class. So the E normally can be represented by E equal to U, H, MH, and then MCP delta T, where here we can say MCP T or the rho VCPT. So this is the term from the energy, how it can be expanded to represent the temperature. So you have the rho VCPT, we substitute inside the equation D rho VCPT over dt equal to the energy coming into the system. So for this part, you have the F1, CP1, T1, and the rho 1, rho FCPT. Plus rho 2, F2, CP2, T2, minus rho 3, F3, CP3, and T3. So this is the complete substitution of relevant term inside the equation. So on the left hand side, you have the rho VCPT. So we know that the rho constant, rho is constant, V is also constant, and CP is the heat capacity, and the heat capacity is like the density where it is fixed value. So CP also constant. So for this part, normally we employ the same assumption where the rho equal to rho 1 equal to rho 2 equal to rho 3. The same goes with the heat capacity, where the Cp equal to Cp1 equal to Cp2 equal to Cp3. For simplicity of our model. So when we have this kind of the assumption, then it make us easier to cancel the term. So here from the d rho Vcp T, we can take it out, the density, volume, heat capacity. Then that leaves us the dt over dt on the left hand side. So based on this, we can see originally there are 4 variables inside the differential equation: density, volume, heat capacity, and temperature. Now, since the volume, heat capacity, density are constant, I can take it out, this variable, outside the differential term. That leaves you the dt over dt inside the differential term. And the same goes with the rho 1, F1, CP1, T1 plus rho 2, F2, CP2, and T2 minus rho 3, F3, CP3, T3. So, based on this, we know that the density is equal with the density 1, density 2, density 3, and as well as the CP1 equal to CP1, CP2, CP3. That means we can cancel it out. So, when we cancel the CP and the density, your equation reduced to V dt over dt equal to F1 T1 plus F2 T2 minus F3 T3. So your equation need to be it's not too complicated anymore. It's straightforward. So less variable involved when you cancel the density and the heat capacity. So lastly, again, this one you can see you have the T1, the temperature 1, temperature 2, temperature 3. Inside the differential term is dt over dt. So this we can assume due to the perfect mixing, the well mixed condition. The T equal to T3. Again, this one has a similar explanation where the T is inside. This is your T. Inside the tank. So when you have the perfect mix, all of the temperature inside the liquid will be equal. And this T eventually will exit into the stream number 3, the outlet stream. So that's why this T3 here and T here will be equal, similar. So in the end, you can obtain the final equation V dt3 over dt equal to F1 T1 plus F2 T2 minus F3 T3. So this is the final form of your energy balance.
So doctor, if we have the Q on the right side, so we cannot
Eliminate.
yeah.
Yeah, correctly. Let's say this one, there is no Q. I put it here. No Q. No Q involved. Let's say in other cases, you found out presence of coil. Presence of coil So you have the Q. So when you have the Q, that means based on this, we start it from this part, rho V Cp dt over dt equal to rho 1 F1 Cp1 T1 plus rho 2 F2 Cp2 T2 minus rho 3 F3 Cp3 T3 plus Q. So you have Q over there. Let's say, just for example, you have the coil inside the solution. This is what you will get, your equation. So when doing the simplification or further rearrangement, this equation may become V dt over dt equal to F1 T1 plus F2 T2 minus F3 T3 plus Q over rho Cp. So you will get like this. So this means the density and the heat capacity cannot be cancelled altogether because the Q does not have the Cp and the density. So this is the case if you have the coil. With the coil and without the coil. And of course the T here can be represented as dt3. So any other question?
Doctor,
Yes.
so basically in test, you ask us to derive ourselves based on the question specification.
Yes, correctly. That's
Okay.
why I emphasize different condition, different mathematical model, different derivation, because you have to do it not only in the test but also in the final exam. All right, now let's move on. So we have the energy balance. So let me write it up. The overall mass, you have the F1 plus F2 equal to F3. For component A balance, component A. So this is your component A balance. So you have component A balance. And then component B balance. And lastly, energy balance. So here we use the without the coil. Alright, so this is the summary, the overall mass balance, component A balance, component B balance, and energy balance. So the next step is variable classification. So in this case, the variable classification, we want to develop the control variable, the manipulated and disturbance variable. So you have the CV, MV, and DV. So in this case, how many control variable do you have? And what is the name of the variable? Anybody?
Two, doctor.
Which are? What is the name?
DT and DX.
Which X?
A.
A. SA3 yeah, and then the T3. Alright. So this is the variable considered as the control variable, the variable that we need to control. Where you have the composition of the A and the temperature. Why there is no level?
Volume constant.
So the volume is already constant. You cannot change the value of the volume anymore. So in this case, there is no level control for your case. Unlike the last week, you have the level because the volume is changing. But here, the volume is already fixed. So how come you can control the fixed volume? So it made no sense. That's why you have the SA3 and the T3. So here you can choose the XB3 as well. But here we just need to control one. You control the SA3, automatically it will be control your XB. So for this part, the manipulated variable for the XA3 will be, we take a look on the component. So in this case, this is your equation where the SA3 here is your CV. The volume constant. The flow rate F1 can be used. SA1 can be used. F2, SA2. SA2 is no longer a variable. It will be a constant one because SA2 is equal to 1. So you cannot manipulate it. While F3 is your outlet flow rate. It's already been fixed. So in this case, your F1 fixed. Fixed or constant. F2 is also fixed. And F3 is also fixed. So how to control it? How to manipulate your SA3?
SA1.
Then, since you cannot do anything about the F1 and the F, because F is already constant, then that leave you the SA1 only. Because F1 is already fixed value, you cannot do anything. F2 is already fixed. SA2 is already being fixed. So SA3 is your target. So that means that leave you the manipulated variable for this case is only SA1. And how about disturbance? What is your disturbance variable?
F1, F2, SA2, F3.
F3 is already outlet. It's already exiting the system. It will not influence your process anymore. So it cannot be disturb your process. What is your disturbance in this case?
F1, F2.
F1 and F2 is already being fixed. Constant value. How come the constant influence your system? So in this case, you need to have a clear understanding. Here the flow rate is already constant. When it is constant, it's no longer considered as disturbance. It's like density, it's like the volume, heat capacity, it's constant value. So it will not influence the system. So based on this, since the F1 is fixed, F2 is fixed, F3 is exiting. It's already exit the system. So how come it will influence the system? So SA1 already select as your MV. So meaning that SA2 here is set as 1 because it's a pure component. So you don't have any choice for the disturbance anymore. That means your disturbance is you don't have any disturbance for this part.
Doctor.
Yeah.
Since T3 also our control variable, will we need to write one more thing for manipulator variable to control the T3?
This one I just here we have two control variable, right? So here I concentrate on the SA3 first.
Oh, okay, understood.
So for this part, there is no disturbance variable for your X because all of the variable has been constant. So if it's not constant, then you can choose it, no problem. So this is the thing you need to understand. Compare your exercise, last week exercise with today, you can see the difference. This is the objective that I want you to learn. Now, we have the SA3. So SB3, it will be indirectly controlled by SA3. So you don't need to include as your control variable. Now is your temperature. So T3. How about this? What is your manipulated?
T1 or T2?
So here, when you do the screening, you know the volume is not going to change. The F1 fixed, F2 fixed, F3 fixed. So there's leave you T1 or T2 only. So which one? In your opinion, which one is more suitable for maintaining the T3?
T1 maybe.
Why?
Because T2 is fixed.
T2 is not fixed.
I think it's both.
Both.
Because T3 is due to the inlet flow rate and inlet got T1 and T2.
In this case, you need to select only one because the pairing 1 CV must be paired with the 1 MV. So which one do you think is more suitable?
T1 because in the stream 2 we have the pure component, so we can constant it for the temperature also, so that we can see how the changing temperature based on the T1.
Okay, all right. Thank you. Thank you very much for all of your response. I'm very happy with how you interpret the thing. Now, here we put some condition. We have two choice. T1 or T2. This is the thing that we can agree. T1 or T2 as manipulated variable. Our problem now, 1 CV must be paired with the 1 MV. So we need to select only one. So the question is which one? So here we have only limited information. I don't provide any data for the T1 and T2. So we don't know. So we just interpret is based on what we have in this kind of the problem. So here the problem is T1 or T2, and let's say if we choose T1, then T2 automatically become our disturbance. The same goes with the T2. If we select T2 as our manipulated, T1 will become our disturbance. So this is the arrangement that we need to use. All right. So we start with the SA first. So before we go to the solution, we take a look on the configuration. So this one is what we call it controller pairing. One CV, one MV, or variable classification. Controller pairing, this is the table. And then what I want to show next is the controller configuration. So in this controller configuration, okay, let me draw the diagram again. So let's say here, this is your blending system. You have the stirrer, you have the inlet, and the outlet. So this is stream number 1, stream number 2, and stream number 3. So in this case, the control variable SA3, your choice only SA1. So you don't have any other choice. So you need to regulate the SA1. So here the SA3, in this case, normally we assume SA equal to SA3. So although your SA3 is located here, you can control it inside because we assume the SA will be exiting as SA3. So here, based on the configuration, CV SA3 manipulated SA1. SA1 located at stream number 1. So when we want to do the configuration, we put it here. Let's say in this case, we put the CT, composition transmitter. C is the composition, T is the transmitter, then you have the dash line, CC, composition controller. So here we want to manipulate the SA1. So this is the location of your valve. All right. So you have the CT, you have the CC, and then the valve. So normally the controller configuration must be tally, must be in accordance with your pairing. You control SA3, manipulated SA1. So it must be tally. So you control SA3 and then you put SA1 over there. So this one is quite clear. Now we take a look on our second control loop where we have a discussion on this T3, T1 or T2. So this is the thing. Let's say we take a look on the first choice. We select MV as our T1, for example. So CV is our T3 and the MV is our T1. All right, now we try to draw the controller configuration. So the T equal to T3. So we assume the T is inside. Okay, here we put controller configuration, the piping line, and then we have the TT, temperature transmitter. Next, we have TC, temperature controller. So according to this, if we select T3, then our MV T1. So the T1 location is at the stream number 1. So meaning that I need to develop the valve add here. All right. Any questions so far?
Can the double valve on the sand stream?
All right. So this is the objective why I'm drawing this one. So let's say you choose T1 as your manipulated variable to control the temperature. As consequent, you can see there will be two valves over here. Valve in this case and valve in this case. One for controlling the composition and another controlling the temperature. So in the chemical process, one piping should be one piping line or one stream must have only one valve. You cannot have more than one. So this is the solid black line is considered as the piping or the streamline. So in this streamline, normally one streamline, one valve. You cannot have two valves. Why? Because it will be conflicting. Maybe one need to decrease the flow rate and another one must increase the flow rate. So it will be violating each other. So this indicate based on the configuration itself, we cannot do anything about the SA1. Because SA1, that is only your variable. That's the remaining variable to be used as your manipulated. You cannot do anything. You cannot choose another variable. So that leaves you to change your temperature. Temperature, you have the choice. Since the T1 here is already used, the valve is already available in the that stream, then you cannot use this one. You need to have another loop. So this one, you need to discard it. So you have the TT. Now TT, draw your TC. Then you need to include the valve at the stream number 2. So meaning that the answer for this case supposed to be T2 as your manipulated variable. And automatically T1 become your disturbance. So this is the solution for the given problem. How to know your selection of variable for MV or is okay or not. You need to take a look based on your configuration. Just remember, one CV must be paired with the one MV. And in one stream, you need to have only one valve. You cannot have two valves. If you have two valves, it will be contradict each other. So I open to any question.
Sir,
Yeah.
at the previous slide, I mean the previous page, F1 and F2 is fixed right just now.
Yeah.
Why is that, sir?
Why the F1, F2 is fixed? Because it is stated in the question. If you read this one, has all flow rate remain fixed. So when it remain fixed, you cannot do anything about it. You cannot adjust the value. This, if you take a look on this exercise, I give different assumption, different condition for you to familiarize. Last week, I didn't state any condition. I just put the value, the flow rate, the variable available in each stream, no constant, and so on. Here is a little bit different. So any other question?
As referred to the controller configuration that we are placing a valve in the pipeline, does it mean that we are actually controlling the flow rate or how's that?
Alright. Okay. Normally, in this case, the correct way is to adjust the flow rate. However, in some cases, for the flow rate itself, we can specifically refer what variable that we want to regulate. For example, in this case, maybe we just regulate the XA1 value. So when we regulate XA1, maybe it's no longer 0.5, 0.5. We can adjust 0.6, 0.4 up to the controller requirement. Of course, when we adjust SA, the total flow rate is also changed. But for this case, we prioritize the composition. It's not the flow rate.
Okay, understood, Doctor. Thank you.
Any other question? Okay, it's already 1:46 p.m. So I know this is the lunchtime, critical hour. Maybe you have another class at 2 o'clock. So this is the end of our lecture for today. So on Wednesday, we will continue with the model solution. How from this obtained model, the derived model, how we can solve the model to obtain the results, the value. Either is increase or the decrease. So this is the next lesson target. So with that, I thank you very much for your kind attention, for your kind response, for your kind cooperation. Have a good day, take care of yourself, and have a good lunch. With that, thank you again. See you on Wednesday.
Thank you, sir.
Thank you.
Thank
Thank
you,
you.
sir.
Thank you, sir.
Thank you.
Thank you, doctor.
Welcome.
Thank you, doctor.
Thank you, Doctor.